Okay, in this session, we'll consider functions of a random variable and some related topics. A function of a random variable will also be a random variable. So, for example, supposing that we have some quantity, some random variable capital B, it takes values small b, and it has a PDF of this form, 1 over root pi e to the minus b squared. Okay, so this is related to the probability of finding a particle of velocity v in a one-dimensional gas at a given temperature. So what's the expectation? Well, if we integrate, if the expectation of v is given by taking the integral of v equals minus infinity to infinity of v times the PDF for v dv. So if you integrate this, you will find that you get 0. Okay. Now, a function of that random variable capital B would be something like v squared. If we want the expectation of v squared, that would be the integral from v equals minus infinity to v equals plus infinity v squared times the PDF for v dv. And if you do that, you'll find that the result is 1/2. Okay, so this is related to the average kinetic energy of particles in a gas. Okay, so now we'll give the definition for the expectation of a random variable. So x is a random variable with some probability mass function f sub x. So x is a discrete random variable. G of x is a function of the random variable, and then the expectation of g of x is equal to the sum over all the possible values of x, g of x times the PMF for x. Okay. And in the continuous case, the expectation of the function of the random variable g of the random variable x, it is given by taking the integral. X goes from minus infinity to plus infinity, g of x times the PDF for x. Okay, so for example, we toss a coin twice and we note the results. Okay, so you could get head, 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 tail, tail, head, tail, tail. And the random variable x is the number of heads that you get. Okay, so you could get 2, you could get 1, or you could get 0. The probability mass function, I think we found before, it takes the value f sub x of x is equal to 1/4 for x equals 0, 1/2 for x equals 1, and 1/4 for x is equal to 2. So what's the expectation of x squared? Okay, so that is the summation. What are the allowed values of x? 0, 1, and 2. So sum from x equals 0 to 2. The function is x squared here. So you have an x squared here times the PMF for x. Okay, so this is 0 squared times the PMF for at 0 plus 1 squared times the PMF at 1 plus 2 squared times the PMF at 2, and that works out to 3/2. Okay, now an important property. So supposing you have a random variable x, and it's got some finite expectation, right? And now you come up with a new random variable ax plus b, where a and b are real constants. Well, then it turns out that the expectation of ax plus b is equal to a times expectation of x plus b. Now, why is that? Well, properties of the PMF and the PDF, and also the fact that when you're doing expectations, you're using sums or integrals, and using the properties. So using the properties of PMFs and PDFs, using the properties of sums and integrals, you should be able to show this for yourself from the definition of the expectation. That the expectation of ax plus b is a times the expectation of x plus b. All right, so if you already knew the expectation of x, you wouldn't have to go and redo all the calculations from scratch for ax plus b. You could just use this property. Okay, and so as an exercise, you should prove this from the definition of expectation and the properties of PMFs and PDFs. Okay, so let's consider this one. You have, again, this thing for the particle and the gas. So f sub v of b is equal to 1 over root pi e to the minus v squared. The expectation, well, you integrate v times f sub v of b from minus infinity to infinity, and you're going to get 0. And then if you wanted, say, mv minus 3, then the expectation of mv minus 3 is m times the expectation of v minus 3 from the previous result. And the expectation of v we said was 0, so that gives you minus 3. Okay, let's try another one. So you roll a fair die, let x, so you have this random variable x, it takes the value +1 if the result of rolling the die is an even number, and x takes the value -1 if the result is an odd number. So what's the expectation of x? I think we would probably expect it to be 0, right? What about x squared? Well, the values that x squared takes are always +1, right? So what do you think the expectation of x squared would be? Okay. Let's try another one. The random variable x is the number of points rolled with a fair die. Okay. Find the expected value of x. Y equals x squared, and z is equal to 2x squared plus 1. Well, note over here, if you once you work out the value for x squared, then the expectation of 2x squared plus 1 will be twice the expectation of x squared plus 1. So you figured out y, you might have to do some calculations, but you don't have to repeat a whole bunch of calculations in order to find z. Okay. The answers that you should get for this are 7/2, 91/6, and 94/3. Okay. So once again, if you know the expectation of x, then the expectation of ax plus b is a times the expectation of x plus b, provided that x has a finite expectation, and not all random variables will have that. Okay. And if you have functions of x, g of x, and h of x, then the expectation of x plus or minus g of x plus or minus h of x is the expectation of g of x plus or minus the expectation of h of x. And once again, you should be able to prove this from the properties of sums and or integrals. Okay, now we come to the idea of variance, which is basically the well, let's see. The idea is that just having the expectation doesn't fully characterize a random variable. So if we were looking at income levels in a country, there might be people with a very high income And there might be lots of people with very low income, right? And then you could have another country where everyone has very close to the same income. They might have the same average, right, income, but really what we should be measuring is how far values lie from the expectation also, right? So variance is a measure of how far you're moving away from the the mean value, okay, or the expectation. Okay, so look over here. I'm taking the expectation of x, I'm taking x minus the expectation of x. So that's a measure of how far I'm getting from the expected value. And then I'm squaring it because right now I'm just trying to measure how far away I'm getting on either side of the expected value. So I squared that. All right. So the variance of x is the expectation of x minus the expectation of x squared. Okay, so that's a function of a random variable. So in the discrete case, that's going to be the sum over all the allowed values of x minus the expectation of x squared times the PMF for x. Okay, what is it going to be in the continuous case? Okay, so once again, the variance of x is equal to the expectation of x minus the expectation of x quantity squared. That's then going to be given, that's a function of x. So that's going to be given by the integral going from minus infinity to plus infinity of x minus the expectation squared times the PDF for x. Okay, and related to the idea of variance is the standard deviation. The standard deviation is the square root of the variance. Okay, so for example, once again, when you flip a coin twice, you record the number of heads that you get. Okay, the probability mass function we found before is 1/4 for x is equal to 0, 1/2 for x equals 1, 1/4 for x is equal to 2. Okay, so then the expectation is given by the expectation of x. The allowed values are x equals 0 to 0, 1, and 2. So sum x equals 0 to 2 of x times the PMF for x. So that's 0 times the PMF for 0, plus 1 times the PMF for 1, plus 2 times the PMF for 2. And that works out to be 1. Now, if I want the variance of that, the variance is x minus, remember x, it's the expectation of x minus the expectation of x squared. Okay, so that's summation x equals 0 to 2. The function of x is x minus the expectation of x all squared times the PMF for x. So it's 0 minus the expectation squared times the PMF for 0, plus 1 minus the expectation squared times the PMF for 1, plus 2 minus the expectation squared times the PMF for 2. And that works out to be equal to 1/2. Okay, so the variance in this case for this random variable x is 1/2, and then the standard deviation would be 1/√2. Standard deviation is the square root of the variance. Okay, now it turns out another way of calculating the variance is it's the expectation of x minus the expectation quantity squared. That also turns out to be equal to the expectation of x squared minus the expectation of x squared. Okay. So if you already knew the expectation of working out the expectation of x squared without subtracting off x minus mu all the time might actually be a little bit easier. Okay, so you should be able to prove this from the definitions of the expectation. Okay. Okay, so for example, if we go back to the same coin flipping twice business, you have the same sample space, the same PMF. Now let's do this. The expectation of x squared is summation x equals root 2 of x squared times the PMF. So it's 0 squared times the PMF for 0 plus 1 squared times the PMF for 1 plus 2 squared times the PMF for 2. That works out to be 3/2. And if we already had that we had already worked out the expectation of x. So the variance of x is the expectation of x squared minus the expectation squared. So 3/2 minus, we already worked out that the expectation was 1. So this would be minus 1 squared, and that's equal to 1/2. All right, so depending upon what information you already have, this way of calculating the variance might be better. Okay. So just as we had the idea of an expectation of a random variable, we have the idea of the variance of a random variable. So the expectation, the variance of g of x is the expectation of g of x minus the expectation. Okay, sorry. The variance of g of x is the expectation of g of x minus the expectation of g of x, quantity squared. And that's the same as the expectation of g of x squared minus the expectation of g squared. Okay. Now, a useful property is that the variance of ax, a is a constant, is equal to a squared times the expectation of x. Sorry, times the variance of x. Okay. So the variance of ax is a squared times the variance of x. Okay, so that's a useful thing to have. Again, you should be able to prove it from the definitions in the discrete and the continuous case of what variance is. And we also have that the variance of ax plus b, a and b are constants, is a squared times the variance of x. Okay, so these properties might simplify your calculations somewhat. Okay, now we come to Chebyshev's theorem. The nice thing about Chebyshev's theorem is that it holds for any random variable. Now you can get tighter bounds if you know more about the random variable. You can get improvements on this, but this holds for all random variables. Okay. And it gives us some idea of the importance of the standard deviation and the variance. So the probability that any random variable x will assume a value within k standard deviations of the expectation is at least 1 minus 1 over k squared. Okay, k is a positive number. Okay, so the probability that our random variable x is lying, it's the value of the random variable x is lying within k-standard deviations of the expectation of x on either side of the expectation. That probability is greater than or equal to 1 minus 1 over k squared. Okay, so what does this tell us about the probability that x assumes a value within 1 sigma of the mean, within 1 standard deviation? Sorry, this should not be mean, it should be expectation. Assumes a value within 1 sigma of the expectation. Okay, so the probability that x lies within mu minus 1 sigma and mu plus 1 sigma is greater than or equal to 1 minus 1 over 1 squared is 0. That's not very helpful. Okay. The probability is greater than or equal to 0. We already knew that. What about the probability that x assumes a value within 2 sigma of the mean? Okay, so the probability that x lies between, sorry, again, not mean, expectation. The probability that x lies between the expectation minus 2 sigma and the expectation plus 2 sigma is greater than or equal to 1 minus 1 over 2 squared by Chebyshev's theorem, and that's equal to 3/4. For any random variable, the probability that something lies within 2 standard deviations of the mean is bigger than or equal to 3/4. Okay, so for some random variables, it will be 3/4. For some random variable, it will be bigger than 3/4, but it will be never less than 3/4. So if you want to make a guess as to what the value is, it doesn't make sense to be making guesses about being, 10 standard deviations away. Okay. Once again, for any random variable, the probability that the variable takes a value within 2 standard deviations of the expectation is greater than or equal to 3/4. As I said, you can get better results than this, provided that you know more about the random variable. This result is amazing because it holds for every single random variable that there is. Okay, see you next time.